So now we're going to move on to section 7.3 and some of the properties we have to remember of proportions. Now this is when we have a win-lose test, pass-fail, black and white, flip a coin. In the case of a coin, when we flip, it has two outcomes, and pretty much very closely, they're 50-50 for either outcome. And we're allowing for the fact that the probability might, on some other operation that we're doing, might be 30%, or it might be 1%, might be anything. And the probability of the first type of outcome relates to the probability of the other outcome. The alternate outcome here is that the probability of the second outcome is going to be probability. It's going to be 1 minus the probability of the first outcome. Okay, these are complementary. Okay, so if you don't get one, you get the other. If you don't get one outcome, you get the other outcome. Okay, so some of the properties is that the sample proportion is going to be the proportion to the entire population. What else do we have here? So then we also have to understand how we're going to get the standard deviation of this proportion, and that is going to be equal to the square root of the proportion times 1 minus the proportion. We're going to adjust that by the number of samples that we have. So this problem here, 7.26, and it's problem 6 in your homework, it's a 6th question in your homework, mirrors problem 1 for the other sampling that we're doing. Now we're doing a proportions test. So the test that we have to do here, these rules apply, these rules hold. If n times p, the number of observations you make times the proportion is greater than or equal to 5, okay, or n times 1 minus p has to be greater than 5, okay? So we're saying that you have to take a watch to see if the probability or the inverse of that probability happens to be very, very, very small. We have to watch out because we have to take a large number of samples to be able to, a large number of observations to be able to satisfy this rule that np or n times 1 minus p has to equal to 5. It's just a rule of thumb that we're using there. Okay, so I'm going to do a quick table here. Let's punch these in. Are all of these valid? Okay, so the first A problem that we have here is we're going to give test 1. This is, let's say, the test of np. And these are your headers here. Test of n 1 minus p. Okay, and so the first one, n is going to be equal to 250. I'll type some of these in here. 100 in the second example, 400 in the second problem, or third problem, and 1000 in the next. Okay, so we want to watch ourselves on these tests. So the probability here is going to be equal to n star p is 0.5. That's like flipping a coin. And then we're going to have this is equal to n star 1 minus 0.5. Okay. And in both cases, they're clearly, you have enough headroom above 5. What is that? It's 25 times larger than 5. Okay, so we're well within a range where np and n times 1 minus p are both greater than or equal to 5. Let's try these other ones out. I'm going to drop these down. I didn't make them generic, so what are we going to take a look at here? We have to take a look at p here in the second one is only 0.1. Okay, so one outcome has a tenth of a chance of happening, and the probability of it not happening is 0.9. Okay, so I'll adjust this equation here to 0.1. Okay, and so notice that p is 0.1, 1 minus p is 0.9 here. So we're starting to get a look at a fact where the probability has dropped down from that 0.5. We have to have a fair number of observations to be able to get above the test that np and then n times 1 minus p is greater than 5. Okay. So here we have n is equal to 400, and our probability is 0.8. So I'm going to adjust my equation there. I could have done this more generically, but I didn't. So I have to punch these in over and over again. Okay, and again, so in the third case, above 5, no problems. But now take a look at this. The 1 minus p here is going to be 0.02. That's a pretty small number, so we're going to have to multiply that by a fair amount. Let's just see what we get out of this. P here is 0.98. Shouldn't be any problem there. Right? Try that again. There we go. And then this is the one we have to keep our eye on because it's going to be a small number, 0.98. What do we get out of there? Ooh, there's a little problem there. See that? We don't have n times 1 minus p greater than 5, so we're probably going to be asked later on at some point whether these are all valid. So what they ask us is keep your eyes open because they're going to look at the empirical rule of normally distributed data concerning the standard deviations, the variance, and the standard deviation variability of the data. Find the interval that contains approximately 95.44% of all the possible sample proportions. Well, I have a sneaky belief they picked 95.44 for a certain reason. Remember what happens in our proportion, these problems with proportion. These problems with proportion, given some number of repetitions here, instead of a smooth normal distribution that we get otherwise, when we do these proportions, it comes out as a more stepwise function of the normal distribution like this. Same idea where the average is going to be the proportion. So if you do 100 repetitions of flipping a coin, if you look at the distribution, if you flip a coin 100 times and you do that test many times, the frequency distribution of that raw data will look like the stepwise function here around whatever the proportion is. So in this case, the probability of getting a heads or tails is easy, or is equivalent, which is 0.5. So it makes sense that if you repeat this experiment 100 flips of the coin, that more than likely you're going to get 50 heads or 50 tails, depending which way you're looking at this. Okay, so down here would be the case where you get, in flipping the coin 100 times, what's the probability of getting no heads on that is almost zero. It's so small on this. Okay, all the way up to what's the probability of getting all heads. Okay, and that's why you can see why this proportion distribution symmetric around the center, just like the normal distribution is. Okay, and that's why we're making these analogies. See, these chapters we're looking at one, now we're looking at the other. So this is what the proportion problem is all about. Okay. And what they're asking us in this is what's the bracket that captures plus and minus the expected value for our proportion that we capture 95.44% of the curve. This is what they're questioning. Okay, so the tip-off should be this 95.44. We'll do a quick test over here. If you're like me, I would suspect that what they're saying is plus or minus 2 standard deviations. And so the way that we do that is, let's take a look at minus 2 standard deviations. And I typed in the wrong problem here, which is the dist. Sorry about that. Okay, so it says our little tail on a normal distribution, the area under the curve to the left of minus 2 standard deviations. That's my hypothesis. That they're asking us, what are the numbers that correlate with this proportion that go between minus 2 and 2 standard deviations? We've got one of them, right? So let's multiply that by 2 is equal to 2 times that. And if we take 100% minus, let's do that again, equal to 1 minus this, we should satisfy our curiosity. And the space between these 2 points, the brackets, is 95.45. And there you go, it's something like that, 95.44, same thing. Okay, for the sake of this problem. All right. And now we have to do treatment. We're going to do the treatment on each of these using the equations above. We already tested out. We know the first three seem reasonable, but the last one's going to give us a little bit of grief right here because n times 1 minus p is less than 5. We can go ahead and we can make our calculations. Let's come up with the standard deviation here is going to be what? Is it going to be equal to, try to get all our brackets right on this, or parentheses. So we need the entire square root of something. And that is going to be p times 1 minus p. So that's going to be 0.5 times 1 minus 0.5. That over 250, which is our n. And have we gotten it? Let's just take a look at what we get as an answer there. That looks like what we're shooting for. So the proportion probability is 0.5, and there's our standard deviation. So if here's 0.5, this is going to equal proportion times, is plus 2 of our standard deviations is the upper bracket. Now we just need to calculate at the lower end of the bracket, which is going to be equal to 0.5. Try that again, is equal to 0.5 minus 2 of our standard deviations, which we'll grab from up here. And that should be our bracket. So let's take a look at what our numbers are. There's 4368, looks good. And we've got 0.5632, that looks good down here. And that gives us, this is really basically a warm-up problem to the proportions type questions.